Hey everyone, it's a pleasure to have you all back here at the MIT IDE for another week of really engaging talks from some of the world's most interesting thinkers. Again, Eric's unfortunately not here, so I'm taking MC duties. Today, I'm very pleased to have presenting Dashun Wang, who's an AP at Kellogg School of Management and the founding director of the Center for Science and Innovation, as well as being core faculty on the Northwestern Institute on Complex Systems. So traditionally, before we start, I'll have I should mention right now, I'm going to have an aside at the end of the talk about how we're going to deal with these seminars moving forward. I already see we have a smaller group than normal because of coronavirus. We have not made final decisions about how we're going to do the seminar series moving forward. We're going to make some of those decisions today. This may very well be the last in-person meeting for a while, so I ask all of you to relish it. All right, Dashun, why don't you kick us off?
All right. Okay, great. Thank you very much for coming despite the coronavirus. Every seminar, as I learned for both you and me, could potentially be the last one for a while. So welcome. So I am very excited to be here. I was asked to do a broad overview talk about science of science, which is an emerging field that many of us now identify themselves to. And I'm excited about this opportunity. And in thinking about what to do today, I thought I'll sample about three broad directions within this field, and then give you some sense of just the flavor of the research and different approaches that we can take, also different kind of data sets that are now available. Okay, so three directions, three type of ideas, and summarizes about 5-6 papers, depends on how you define them. Okay, so what is science of science? This is a broad 1-minute intro of the field. So science of science, 2018 was an exciting year for the field because we published the first review paper, The Science of Science in Science. And Nature was very pissed about it. And then later that year, actually, Science doubled down with a special issue, put us on the cover, called World and More Scientific Science. A lot of the MIT folks are familiar, as well as the HBS folks. And we're also looking forward to the first book of the field that's forthcoming this summer from Cambridge University Press, which hopefully summarizes the different opportunities that we now have. And this has been my major part of my life for the past 4 years. All right, so what is science of science? I think in many ways, the idea of trying to understand science is not new, okay? So this is an idea that started in the mid of last century. There are many founding scholars in the field across different kind of disciplines. For example, there's Robert Morton, the great sociologist of science, to think about the idea of Matthew effect, singletons and multiples. Gosala Price, that's a physicist turned historian of science, to think about the idea of invisible college, power law, or cumulative advantage. Or Harriet Zuckerman, another sociologist of science, to think about scientific elites, or Thomas Quinn, to think about paradigm shifts, by the way, another physicist. I think in many ways, what we're trying to do now is to stand on the shoulders of these giants and then take two things that they did not have the luxury to have. Number one is a massive amount of new data sets that now become available to us that captures the entirety of the scientific enterprise. And these data are becoming available at a rate that is quite remarkable these days, because it feels like every year my group is driven by a new data set that became available that we couldn't even imagine just a year ago that this is now available. And that's true this year, that was true last year, that was true a year before. I think over the past 5 years, this has been a consistent pattern. So as you know, science is driven by the invention of instruments. So in many ways now, as computational social science, the instruments are data sets. So that's very exciting. But I would say the second force is why the emergence of this multidisciplinary field is the parallel developments in fields like AI, data science, complexity sciences, which I will show you a few things about what we are able to do now with the development of AI to operate on these data sets that we couldn't quite do before. So what the fields offer us is a set of highly scalable tools and techniques that grow in accuracy and robustness and actually improves rather dramatically over the years. So then they can also now all these tools and techniques and feedback can help us make sense of the data. So I think the combination of data and tools together, it seems to tell us over the past few years is that they can tell a rather complex but rather insightful stories about how innovative careers unfold, how people come together for innovation, and how scientific progress can emerge from multiple interconnected factors. And oftentimes in business school, this has been captured major imaginations across several business schools. I think part of the reason is oftentimes we realize they have potential implications for entrepreneurship, for sustainability, for business innovations, right? So what I'm gonna do today is to sort of sample 3 different directions we've been exploring, which then grow, each of them take their own life now as basically subfields within the field. So just give you a sense of the different questions that we can ask, all right? First question is what I call the hope project, is to think about this idea that are there patterns of a promising scientific career? And the overall arching question to me personally is to think about this hope question is, when do you do your best work? And will you produce a higher impact work after a major discovery? In other words, is there any hope left, or are we dead, scientifically speaking? So that is a very personal question to me. So we started to explore this with Roberta Sinatra, a fellow researcher, co-author. And we first realized there are many ways to look at a career, but one view seems to be actually quite simple and consistent, is to represent a career in this job pin type of view, okay? So the way we were looking at this is to say, well, for each paper you publish, how well does that paper do? And in this case, we measure 10 years of citations adjusted by time, inflation, and field. And then if you do this with everybody's different job pins, then there's a clear question, because there will always be a pin that's the highest, okay? So the question is, when do you do that work, okay? So that's the first question we wanted to ask, the timing of your best work. So this is a question that has fascinated many, many people back to the 18th century, and many economists and psychologists have measured this. Consistently, what you see is this kind of pattern, that you do your best work in your mid-career, somewhere between 30 to 40 years old. The idea is, in the beginning, you have to learn. There's no a 4-year-old has won a Nobel Prize, because you have to learn, right? And then your innovative career start to blossom, and then later on you start to have all those kind of duties, responsibilities that piling on your shoulder, that decreases your chance to produce, to devote to research. Okay, so this is basic conventional wisdom, and we validated in our data set. But here we wanted to take a slightly different spin to this measurement. We were hoping to say, well, instead of measuring when it occurs in terms of your age or in the units of time, what if we measure where it occurs in the sequence of papers you publish? All right, just a slight spin to the problem. And we want to do this then not just for scientists. We realize, well, there's actually similar fashion you can think about artists in terms of the artworks they produce along their career and the auction prizes of these artworks, or film directors in terms of the movies they produce over the career and how well these movies do in terms of, for example, IMDb ratings. And we're going to measure this quantity I call Ni over N, which is out of all the papers you produce, out of this sequence, which one is the best work of your whole career? Okay, so is it the first work, or somewhere in the middle, or last work? And I want us to think about this also, not just for your best work. I can do the same measurements for your second best work and third best work and measure this over. And what we see is that you see first out there on a cumulative distribution, you see this follows pretty much a straight line. No matter which career you look at, and no matter which is its biggest hit, second biggest hit, or third biggest hit you look at. Now, if it's a cumulative is a straight line, that means the probability distribution is a flat curve over the sequence of work. So what this means is that this is what we now call the random impact rule. It seems to say, well, although in terms of age, you tend to produce your best work in mid-career, in terms of the sequence of work you produce, it has an equal likelihood to be your very first work, very last work, or somewhere in the middle. So this results then generate a lot of discussions, and because a major consequence people seem to take away with is that there is hope. So what this seems to say is that, you know, as you grow older, even though the chance for a breakthrough seems to start to dim, but that's only because you publish less. And for conditional on publication, per paper hit rate appears to remain constant over the career. So there's a lot of people then seem to take away from this. Hopefully, if it's useful for some of you, is as long as you keep producing, your best work may be yet to come. Okay. Yes.
Does that conclusion actually fall? Because there is some kind of data generated in the background where people's decision how much to publish depends on past outcomes. And what they're saying is that, well, if you just work harder and publish more, you may still get a big hit. But that it would be a very different data generating process. This distribution and the fall.
It's true. It's true. What the data shows us is that the quantity seems to peak in the middle, and the quality per quantity seems to be constant. It could be a selection effect as you go older. You know, you'll be more selective to publish. Although that's we don't have a model yet that can exactly produce that selection that's exactly offsets the decay in terms of quantity. So we don't know that yet, but you're right. So this, yeah.
This is like physics. There are many authors usually in the paper studies. How do you deal with that when you want to study at a particular level?
Yeah, so there are a couple of ways to the data processing. One way is to only consider lead authorship papers and then redo the analysis. There is another actually a PNS paper about figuring out your relative credit share within the paper. So you can actually then do the fractional credit for the papers to control for authorship. So we did that, and it remains robust against authorship. Okay, so so this raises a lot of questions, and one of them piqued my attention because one question it raises is that it seems like everything is random, then paints a very random viewing creativity, then raises question of what happens if you actually have a breakthrough, because the Matthew effect also suggests that if I produce a big hit, you know, it brings attention, brings resources, and also I feel like I learned some tricks. And that should help me produce another hit down the road, right? But if your biggest hit, second biggest hit, and third biggest hit are all appear by themselves at random, that seems to say, if I produce a big hit, there's a regression toward the mean story. The next one actually may be worse if everything is random, right? So that puzzles me for a while. And then so the puzzle crack open when we look at the relative position between your biggest hit and second biggest hit. So here we measure, given I know where your biggest hit is, where would your second biggest hit be? And we measure this across all the three careers. What you see is a diagonal pattern start to appear. So this seems to say that once I know where your biggest hit is, I know actually quite well where your second biggest hit might be. It's just around the corner. Another thing to observe is that this pattern seems to be quite symmetrical around the diagonal. So it's not like your biggest hit type more likely or less likely to occur before or after the second biggest hit. There seems to be also equal chance to occur. Okay. Now,
just ask a question about
yep.
what colors mean. Are they?
So you can calculate joint probability for timing of biggest hits and second biggest hit, then normalize for the probability for them to each occur at random as if independent. And then this color would mean the relative probability for real data to observe relative to random expectation. White is about expected, and then red means a lot more than expected. More than expected. Blue means less than expected. Yeah, like it was, this is a Maslow plot, which we will be familiar with. But in this case, it's easier because the null model of x, y axis, they are also random by itself, right? What I talk. So it's easier. But in other cases, it will be the 2002 science paper by Maslow type of approach.
I'm sorry, I'll leave the University of Chicago. I'm not surprised by this because, first off, if there's a breakthrough, what happens in the history of science indicates when there's a breakthrough, a bunch of people cram into the area.
Mm-hmm.
So cold fusion, the invention of the transistor, different kinds of physics, machine learning.
Yeah.
How do you adjust for the faddish cascade, the attraction, and indeed on a funding adjustment basis? How do you adjust them? Because naturally, I'm going to get more, this field is going to get more people involved, and there'll be more citations as a natural part of the rise of the discipline, as opposed to the quality of the work.
Yeah. So, so that's a very good point, which I will talk later on about what exactly generated this. But just to on this point, I think that this, if we had known this results the first try of the data, it wouldn't be surprising. I think what was surprising was in the context of this data, where the biggest hit is random, second is random, third is random, and then now add more nuance to this. Each of them appear random, but their relative timing turns out to be quite predictable because they are actually relatively closer. And just on that point, that you can repeat this between second and third, first and third, and you see it's all this kind of a diagonal pattern. So what this seems to say then is, while the timing of each hit appears random, their relative timing follows actually quite predictable patterns. This is what the data shows right now, and I'll explain what are the models can explain this next. Is this, so more questions?
Yeah.
Yes.
So it's not always clear that a scientist knows when something's hit, and how it gets to that point. What the curve is, right? There's variation. Like there are sleeper hits that are hooked for a while, and then they explain later. So if you look at those examples, you can see that someone gets feedback about how important it is at a time that's varies with respect to when they produce.
Mm-hmm.
Are you able to see how much the feedback matters, or?
We don't know the feedback. The broad question of this idea that in baseball, if you hit a home run, the guy doesn't really run very fast to the first base. So the idea is you hear the crack, you know it's going out of the park. So the broad question of whether that happens in the creative careers we look at is an open question, something that we're very curious about.
Citations are informing feedback.
They take a long time to improve.
Yes, but it doesn't happen immediately, right? So I'll show you how long does it happen. This is the idea of Hall streaks, and then we will talk about what may explain Hall streaks, which, by the way, is something, the new data I'm just present this first time I ever talk about it. It's for a long time we don't know mechanism, but I think now we have some new answers, so I wanted to add it. Yeah.
Do you have a way of judging if two sheets are really two separate constitutions, or if the same things are in parts?
Right.
So
yeah.
If I told you that War and Peace Part 1 is a very popular book that Tolstoy wrote, and then it's War of Part 2 equally popular.
Yeah.
That's not useful, but if you say that
So
two completely different genres and then both, yes, that's the.
On that note, very good point. One of the mechanisms we're testing is, it's not really Hall streak, it's because your dumb luck stumbled upon one idea and you publish 10 papers about it. So the War Peace Part 1 and Part 2, which one you think will be more impactful? Sure, Godfather 1, 2, 3. Which one would be the biggest hit? Godfather 2 is the middle, right? Or if someone should be. Right. So then in the Hall streak model, we should see some fell off before it completely disappear, which we don't see. By the way, that's kind of just when we have the new mechanism, then we can ask the data to see if this is consistent, which I'll show you a little bit more. So this is new evidence. Now let's talk more about the overall. So one way this could happen is that this is a variance story. It's just an increase of volatility instead of on average is a lift. Okay. So one way to think about this then is let's look at winning streaks. Let's draw an artificial line for each career and look at how many consecutive works that you have all above that line. Okay, if it's just a volatility story, then you will not. It will be just as much as we expect at random. What you see is that in real data, the streaks is systematically longer than you would expect. Okay, so what is the data now seems to reveal is a cluster of hits. The hits in your career seems to tend to cluster together in closer succession than you would expect at random. So the question is, what mechanisms are responsible? So, and it turns out, so we proposed one model that at least was sufficient to explain what we observed. So is to hypothesize that it could be in a career. There's a you can think of a career as you're starting out your career, and then you have a certain level in your how good your papers tend to be or your movies tend to be. And every time you publish a paper, you draw from a fixed distribution. Okay, you progress along your career, and at a certain point, and this is a random point in your career, all of a sudden, you're elevated to another level, like you went super saiyan, like you're not yourself anymore, and you sustain in that level, and sort of now you're drawing from a different distribution, and sustain on that level for about 4 to 5 years, and then you fall down to where you were before. Okay, so it's a very simple a very simple modification of the latest model on careers. And now the question is, does this reproduce? Think about this model, does it reproduce what we observe? And it did seem like reproduce at least all the phenomena that we know about careers, which then raises a very interesting question is, if we actually do a maximum likelihood inference on real careers with this kind of a model hypothesis, then would it tell us more about what are the characteristics of house streaks for real careers? So we did that and fit it to 3 different kinds of careers, and we got some interesting data that could be useful for all of you. Okay, so first, we find that a house streak is quite ubiquitous. For each of the careers, over 90%, or about 90% of people have at least one house streak. Second is usually unique. For most of them, people just have one house streak. There could be people have 2 house streaks. For scientists, it's about 25%, artists is about 30%, but people have 3 house streaks are all exceedingly rare.
The definition of a hot streak, again, is?
It's a short period of time where you deviate from your sort of typical
size of the
distribution.
deviation?
Size of deviation, you can then measure and look at, like.
So what is your size of deviation? Is it 1 standard deviation, 2 standard deviation, 1.5? What's the deviation here?
2 standard deviation.
2 standard deviation.
Yeah. Okay. So and then if you look at the how long does it last for the house streak? So you see it doesn't last forever. It's relatively pretty localized. For film directors and artists, it's about 5 years. For scientists, it's about 4. And interesting, if you look at how many papers or art paintings you produce during house streak, you see you are actually not producing more than you would expect. So it appears to be unassociated with productivity change. So what this means is during that period, you don't produce more or less. Your productivity seems to be stayed the same, but just what you produced seems to be better. Okay, so then we realize that if we understand the some new patterns about career, then would this help us to explain this curve that we all look at, which is on Google Scholar, right? This is sort of captures your cumulative impact of your career. And this is combined with an earlier paper I published in 2013. We're trying to understand the citation dynamics of individual papers. And then we thought, okay, so if I can understand how each paper is cited, then this is a cumulative of all these papers. And if I understand the overall dynamics of how these papers seem to be, or if there's this period that seems to be better, wouldn't we have an analytical solution for the Google Scholar curve we observed? And that is the solution. So then we have an analytical solution, and you can actually fit it to all the careers. And it seems to be working quite well. So then this finding then raises a whole range of questions now, because if house streak is ubiquitous, and is relatively unique, it seems to have implications for personnel decisions, especially in science, that your projected future impact is very crucial. Think about you're hiring someone, junior or senior, you're trying to give a grant to someone, then the future impact is always very crucial. But we're showing that the productivity in the career can be uneven. So then it raises the question is how do you operationalize this? Okay, so NIH now have a working group is trying to figure out how do we time this. When they found it, they were like, this is the best thing ever happened because they were like, oh, 4 to 5 years. That's like how long our grants seems to last. So imagine if we can just capture everyone's house rate. And we run the data, it seems to be actually more nuanced.
8 years and see if that changes house rates.
Yeah, so no, Francis Collins was, when he saw it, he was like, you know what? I know what caused the house rate. It's because our grants. So can you, so this is, I intended to present this, but it's a fresh data. So we then go ahead, they funded us and we go ahead, run the analysis to say, let's just see everybody's house rate when NIH grants happens. And we see the NIH grants precisely happens after you are finished your house rate. Makes sense, right? Okay.
So if you go back to this earlier point, that it could be that we're just lucky because it will enter an area before it becomes a bubble, and then we'll write that. How would you run that?
Yeah, so the next question, so we have a lot of discussions about how to operationalize this finding. The major limitation is that for a long time, we don't know the major, any provable mechanism from data that can be validated from the data that correlates with house streaks. And we tried in the Nature paper we published, reported this, we tried about 5 different mechanisms, and each of them actually quite plausible. For example, the idea of serendipity is, you stumble upon an idea, and then you do multiple papers, and then it's gone, so you're back to your normal self. Or the idea of collaboration, it's not really your house streak, it's really this amazing postdoc that's now at IDE and do a bunch of papers for 4 or 5 years, and that person's gone. So so there's a different mechanisms. Each of them actually quite plausible. We tested them, and they are inconsistent with the patterns we observe. And now I want to show you a new evidence we have. For a long time, we finally, now I think we have a new mechanism that seems to be pretty robust against different chance, which I will talk in 1 second after his question.
One quick comment. What I would do if I were advising would be to say, we should use fraud as an example of this to test these things. Where has fraud been uncovered, and see how those things get used and how fraudulent papers got cited. The second, I'm sure you're excruciatingly familiar with, is the reproducibility crisis in social sciences, where you can literally see things being cited by default, but there's no real replication, and so you have a subsidy. You have let's create a phrase, a citation subsidy, where people are citing things, but there's literally no underlying validity to it.
Yeah.
To the citation or to the written word?
To the citation, which is being used as a proxy for hot hand.
Okay, so just
only in science, so not in the
right. So just to clarify, we did repeat, or within science, we repeat our results for different disciplines. So it does hold for different disciplines, and then that could work for science, but not clear for art or film directors.
Right.
Why that would. But so the question then is, what are mechanisms that can actually operate across domains that can explain what we observe?
Sorry, but I feel like you missed maybe the major point there, which is that you have 2 things going on. Right? You have someone getting feedback about how well they're doing, and then you have the actual quality of the work. And that's confounded, right? And so the way you can break that confound by looking at a case where the quality of work is low, but in fact the signal is high, like in a case of fraud. Right?
I see. Okay, got it. We have the data, by the way, the retractions, although we want to make sure it's exogenous instead of endogenous.
But also, you could just do fixed effects, right? You could basically say, let me control for the fixed effects associated with the keyword. And it could be that some keywords, you're just looking at what, if you just have those keywords in the article, you get twice the citations of an average article. And that's going to adjust to the edit.
Mm-hmm. Fix, so topic adjustment of the, yeah, so would the controlling sort of separate the analysis by fields help a little bit in the topic or not quite? You think we should further adjust it?
It depends what level of granularity, but it seems like within those different fields, there's also different you can say.
Yeah, okay.
And the areas go in and out of fashion at the time, so you want to capture the base on.
Got it. Okay. So thanks. I should write down some of these. Okay. So I'll remember this. Okay. So one question is what's the mechanism, and one idea I've been trying to explore is the idea of whether this is associated with exploration or exploitation, which is a creative strategy that can operate across domains. Okay, so if you think about the essential tension by Thomas Kuhn, it's about the careers by exploration and exploitation. Exploitation helps you go deep. Maybe that explains the house streak, or exploitation, exploration explains house streaks because allow you to take risk and try different untested opportunities. Okay, so to do that, then we need to have a computational methods to see through each of the work and get deeper into what exactly is this work. Okay, so that for science is possible to do. Actually, thanks to a paper published last year by somebody else, is to look at the co-citation network of all the references. So if you think about all the references of each paper approximates the topic of sort of what this paper is about, then you can, this is a one person's career, then you can look at all the co-citing network, how these references are co-cited by others, and sort of proxy which references are closer. Then you will see, like along your career, there are different kinds of topics and different kinds of patterns for each paper that you publish. And you can actually map that out for each individual. You can see initially begin the career in the right space, and then before the house streak, it seems to have a whole bunch of studies. And during the house streak, it concentrates in this yellow part, okay? So this is when we initially begin to see this. But now the question, the challenge is what happens to art? What happens to film? How do we do that? So that for 2 years, we finally now figure out one way to do this. The way we did it was to collect a brand new data sets of all the paintings as an image. So it's 800,000 paintings. And to me, we took a long time for us to collect it. So these are images. Then you combine with VGGNet, which is the computer vision image recognition. And with VGGNet is pre-trained, so it can recognize as a portrait or different objects. And then you have a fully connected layer afterwards to classification out of the output of VGGNet. So basically, you combine two neural networks to then capture both. So these are a fully connected layer and max pooling layer. So if you look at a fully connected layer, then the layers close to image gives you the low-level features like a brush stroke and things like that. And the layers close to the output then tells you about the overall style and object. Okay, so then sort of if you combine these factors and do a whole high-dimensional embedding of art, and we're hoping to see then if we can capture something about where you are, what is this art, what are you trying to explore, similar to the idea of research topics for scientists. We did the similar, so we had to invent our own method. As you know, there's no people really care about this before. So for films, then what we did is to collect all the plots combined with casts, sort of this two major information, which we think could be informative. For all the plots, then we do word-to-vec type of embedding to embed all the plots data set, and then construct a co-casting network of who appear together, so captures who would play the film. So this is a plot line versus who plays it. And then you can do a network embedding of this co-casting network. Then you basically then train this neural network. You have another just high-dimensional representation of each film. So you embed then each film or each artwork into 200-dimensional space. So give you a sense, Jackson Pollock, whose house streak happens in what's now called the drip period. Okay, so if you look at Jackson Pollock, this is all his paintings. Before house streak, you see he was exploring all over the place, all different stuff. During the house streak, it all of a sudden become a lot more concentrated. We know this is anecdotes because all of a sudden it's all about streak. Okay, Peter Jackson, similarly, you see before the house streak is doing all kinds of different movies. And this is sort of the high dimensional, 200 dimensional projection on 3-dimensional space. This is the only way we can visualize this. And then during house streak, you see start to have this lot of ring series about that.
I just have to ask, though, Jackson, I need to understand your ontology of huts. So Jackson Pollock, whether he likes it or not, is the hut streak a function of the reviews? Is it the auction price?
For Jackson Pollock's auction
It's
price.
Purely the price.
For this
So
one,
if
yes.
I can demonstrate to you that Jackson Pollock had cut a deal, a surreptitious side deal with a couple of art dealers to do things, that blows you up.
Sure.
Okay.
Yeah. So sure. It's a very controversial, by the way, just the idea of quantifying how good
Right.
the artwork is.
That's why I'm asking.
Art price has a lot of its own problems. I mean, I'm not an
It's a good
artist.
University of Chicago kind of, so I like that price.
That came out of University of Chicago. David
Of course
Glenson
it did.
is he's so. Yeah.
Question. Can you go back? I mean, with these
This inviting or this inviting?
Yeah, sure. So, are these basically autoencoders, or because I see at the end you have some PCAs, and then you're showing me that like this correlates with the presumably labels that have been ascribed to known artists, like impressionism or expression. Like these are categorical genre labels or something like that.
Right.
Did you assess the extent to which you can predict those from? I mean, is this an autoencoder where you train it to recreate itself, or are you training it to
predict? So for this one is to predict the art labels in the end. So then
So you have the labels for some, and then you're doing it for many more?
For these images, artworks, we have the labels for what's the art style. So
my point is, why are you trying to get an embedding for the artwork if you already have the labels, or you only have the labels for a small subset of them?
Well, because you are hoping, ideally, you're hoping to have some representation of what this artwork is about inside of just art style. So similar to publications, you have disciplines, but you want to see, what for each discipline there's higher granularity. So this is a similar idea of this is, there's paper has its own tax code, and then why don't we just use that, because it gives you more combination if you actually go through the references and what each paper is about. So that was the.
If you'll forgive the introduction here, you had that in psychology and economics with Richard Thaler citing the Yale, Kahneman, and diversity papers, meaning effectively behavioral economics. They weren't published in economic journals.
That's
they were
right.
published in psychology and behavioral journals.
Right.
And he imported them into another discipline.
So hopefully then in these references, then you can see where do you draw the knowledge from. And so that's kind of similar to this is each artwork has an art style that's labeled, but then, yeah. So, but, again, this is, very fresh. We're just, we wanted to see, well, the big question then is now we have some representation. The predictive accuracy is high, but the validity is questionable. But then to our own purpose is how does this then correlate your trajectory on this high dimensional space? How does it correlate with house streak? Okay, so we just did that to think about if we feed everybody's house streak. You see this kind of type of model. This is a real career selected, cherry picked by for different people. And now, what I can do, then you just repeat the analysis before the house streak and during the house streak, and see your overall entropy on this high dimensional embedding space. Okay, so what we see in the conclusion of this slide is that turns out neither exploration nor exploitation by itself explains house streak, but a combination of exploration followed by exploitation seems to closely, that transition seems to trace when house streak tends to start. So And that's now start to motivate my own way of doing work. Hopefully this is useful for some, yeah. Yeah.
So the entropy that you're measuring in these embedding, you have embedding vectors.
Yeah.
And you take a collection of embedding vectors and say, what is the entropy of these embedding vectors, by which you are basically estimating the kernel density, like what volume of the space they take up, or what is the exact measurement?
Yeah, so in this case, for example, you can do different clusters.
So you do a clustering,
yeah.
the entropy is based on belonging to
different clusters, and then you can see your relative commitment to each cluster. Right? So similar to this, science is easier. Let me explain science.
It's what the weight is within each cluster.
Yeah.
In that
So science is familiar case. So imagine these are different fields, topics, and this will be of completely committed to just one topic, and this will be a higher entropy case where you're basically all over the place with everything, all different kind of topics. And then this, again, then it's more concentrated. So it corresponds to more exploitation in this case.
By the way, where you don't have to intermediary clustering to estimate the sort of, because the thing you're trying to estimate is what is your spread throughout this space, right? Given some collection of these points. And I think you can do that without having to resort to doing clustering.
I see. So these sort of.
Take the trace of the covariance matrix, for example, of that set of embedding vectors, right? I think that would be perfectly reasonable estimate. Or if you wish, do SVD and the sigma matrix, sum the diagonals, right?
Okay, sounds good. So no, that's we've been thinking about this. You're right. So we should try that at least. So we tried after the clustering, then we tried different kind of entropy measures, a whole bunch of them that people tend to use, Gini impurity, for example, and but we haven't tried to think about without clustering. Then maybe we can also do something. Yeah.
It just seems like there's so many somewhat unnecessary. Equations already set.
Cool. Yeah.
So is one way to think about this kind of like all these people are effectively mining for gold. They're searching certain areas, they happen to hit something valuable, and then while they're exploiting whatever they find, they're also hunting for something at the same time, just a little bit less of an extent. So if that's the case, then and I think of some of the folks who get multiple hot streaks as being, say, more optimal bandits, who are really good at finding multiple things and doing that trade-off properly, or is it?
Yeah, so a very good question. So a couple of comments. So we repeated this just for the second house week. For people who have second house week, you see the same pattern. Is like this cycle of, and I think what's important to think about is both behavior seems to be strategic because both behavior exceeds your typical level. So that means before house streak, you're exploring different things, but you're exploring in a manner that is more exploitative. You explore a lot more than your typical. So in this period, we're trying to try different things, trying to look at a different kind of style or different topics, and then you become very focused all of a sudden, and a lot more than your typical as well, and just try to focus on this. And what we find is that this topic, then there is the question, okay, can we predict, and out of all the topics you explored, which one you should exploit? Like, as a service for NIH, then they know hopefully what to fund. But it turns out to be what you tend to exploit is not the last one you explored, all right? And it's also not the most popular one at the time that you explored. So this seems to suggest in some strategic of looking at, this period of past 4 years, I've been trying a whole bunch of things, something to speak to me, something not, and then I'm gonna pick one now. I wanna I wanna try to focus. So that's kind of
what the contrary to NIH might want to fund more exploration.
That's right. They want to fund either exploration or exploitation, but
an externality where people maybe exploit more than they should.
Yeah, and hopefully then now people think about this combination of A/B punch of exploration followed by exploitation could be useful. Yeah, go ahead.
Well, the one thing I was saying that there may be some sort of disciplinary arbitrage you could pursue. Let's take the NIH for example. You have clinical research and therapeutics. but at the same time, what we've seen in the last 15, 20 years is the emergence of translational medicine. Which co-author clusters appear in all three? Who has had a hot streak in all three citation domains? So you have a guy like MIT, Bob Langer, you know, so he's everywhere. So it would be an interesting thing to see who has hot streaks in multiple domains in that regard, and that can be an adjuster. Are the mechanisms the same in each of those disciplines, or are they different? Are the clusters similar, or are they different?
Yeah. So first. Domain difference.
Because your point is a better one, which is the real issue is what's the signal. So we have to figure out what are the signals and where those signals appear. Applications, auction houses.
I mean, independent of quality versus popularity brings to the table, because I think everyone knows that when you get a big hit, it then suddenly becomes very easy for you to publish at a lot of places.
Right.
So the question is, are people citing you because they know you from the big hit, or are they citing you because the quality of your work is high, right? And I think it's hard to disentangle.
That's the Matthew effect for Merton.
Right.
Right. So no, I don't, in some sense, I don't really care to entangle it, because to me, it's like I see a lot of people based on their judgment on citations anyway. So I just want to understand what are general patterns about citations.
But then you need to look at H-index and Garfield and those
Well, they can't respond to citations because it takes too long for them to recruit. But they can, I mean, they get it. If you want to assess your own quality and then say, do people continue their hot streak? How do they even know it's a hot streak?
Well, yeah, so that's the question. Do you know, I've actually been interviewed casually for people. I know their hot streaks, so I just say, hey, from this period, what's your recollection? You know, I had this conversation with Sandy yesterday. But, you know, there's some people say, yeah, I have some sense, but never thought it would be that big. Or, yeah, so it's definitely, this baseball analogy. So I've been asking Saul Perlmutter, for example, when he discovered this supernova, you know, did he see, you know, it's going to be who he is today? You know, he's like, well, you know, some of people can tell, some won't. So when do I need to stop?
Well, we usually go until noon or 1 o'clock. So why don't you? Yeah, you have another
10 minutes.
10 minutes.
All right. So let me sort of just do one more study. Is to think about another direction. Well, one major limitation of the previous direction of research, which is growing by itself, to think about careers, is that nowadays we don't do things by ourselves. Okay, so the big discoveries often come with a complex network of people working together. One of the most foundational paper was published by my colleagues, Brian Woodsey, Ben Jones, together with Stefan Wutzke in 2007, is to document this remarkable fact that over the past century, one of the most universal shifts in science and technology is the growth of large teams in all areas of research as solitary researchers and small teams diminish. Okay, this is a trend that seems to very robust across domains. And one of the poster child example would be the Ligo experiment, which detected gravitational waves. As a recurring physicist, I kind of get a little excited when I talk about this. But if you think about this, it's a so the Ligo experiment is 2 arms of tunnels. That's each of them is 4 kilometer long, and that's housed in an ultra high vacuum that try to detect a variation that is 1 trillionth of an inch. Okay, so it's definitely a feat that no small teams can ever pull off. Okay, so this is the largest project ever funded by NSF. And when the paper was published, it has more than 1,000 authors on the paper. Now, partly thanks to the robustness of this shift, the overall transition toward large teams now actually become a self-fulfilling trend. For example, there's evidence to show that for NSF, when there's a large team and small team applications, if they're equally qualified, people are more likely to fund large teams, partly because of this insight, okay? But on the other hand, there are also reasons to believe that maybe large teams are not optimized for discovery, because the business literature will tell us, you know, large teams, just like large business organizations, tend to focus on sure bets with large potential markets, where small teams that have more to gain and less to lose are more likely to undertake untested opportunities. So this is sort of prompt us to think about, are there differences in the work that were produced by large and small teams? And we did this in 3 different settings. Number 1 is to look at about 40 million papers published in the past 50 years. And here I'm focusing on really just the past 50 years. And in terms of citations of the papers, and look at the team size within each paper. Second is to think about inventions. So look at the patent database, around 5 million patents and their citations. And third one is a software product, is to look at about 16 million GitHub projects. Look at how many people contribute and how well they seem to do. Okay, so 3 different settings, and across them, I'm gonna measure use this measure that was developed by Ross Wang and Jason Owen Smith back to 2016, is to measure, in addition to the citational work, I want to think about whether the work is more developmental or disruptive. Okay, so what this measure, D measure, is trying to do is look at this focal work and all the references they cite, and look at when this work is cited, do those papers also reference the paper that this paper cited? Okay, so think about this paper. This is the BTW paper. This launched the whole field of self-organized criticality, BTW model. So very disruptive paper. And if you look at this paper, all the future references, all cites just this paper and ignores all the references that this paper built upon. So in some sense, then this is sort of an indication that this work seems to eclipse the prior literature that it builds on. Whereas this paper is Davis et al., which won the Nobel Prize in Physics. This is empirical validation of Bose-Einstein condensation paper. And you see this paper has the same amount of citations, but these citations all also cite the paper that this paper built on. And so what this suggests that this is amplifying the existing literature instead of creating, sort of eclipsing the prior literature. So in this case, we'll call this developing papers. And in this case, we'll try to call them a disruptive paper. So not my measure, somebody else's measure.
In terms of normal science paradigms.
Yeah, well, it includes everything, yes. Okay. Includes everything, right. Morgan is now trying to, Morgan Frank, who is not here, he's trying to look at the paradigm now too. So, okay, so now if this is a simple measure, now let's just look at across all these domains. As team size start to increase, what's the trend? So what you see is the right curve all increases, and this confirms all existing studies, although now it's across 3 different domains, that as teams grow larger, the work they produce tend to garner higher and higher impact. But when you look at the green curve, it systematically decreases. So what it means is that as team gets larger, the disruptiveness of the work they produce systematically decays. Okay, so what then seems to suggest is that whereas large teams tend to develop and further existing ideas and designs, their smaller counterparts, the small teams, tend to be the one that disrupt current ways of thinking with new ideas, inventions, and opportunities. So in other words, in this case, it seems to say, large teams excel at solving problem, whereas small teams seems to be better positioned to propose new problems to solve. Now, close the loop to think about the gravitational wave example, then you realize, well, the detection of gravitational wave is called the discovery of the 21st century because it validates the discovery of the 20th century, which was the paper proposed by Einstein. But when that general relativity theory was proposed first to Prussian Academy of Science, there was only one person in that paper, which is him. So, and this, obviously, this is the first order effect, then raises a lot of questions about robustness check, is to say, well, is this really a small versus large team? Could it be a difference in terms of disciplines? Could be a difference in terms of topics? Or is a review paper versus non-review paper? Or is a theoretical paper versus empirical paper? Or maybe it's because people are different. Some people like to be small teams and they are better. And some people like to be in large teams, they're better at doing something else. So we tested all of them. In particular, we spent a lot of time to think about this individual fixed effect, where we look at the same individual across the data sets, for same individual, when you shift from a small to larger team, you see the work you produce systematically become less disruptive. So what we see is that these factors overall accounts about 40% of the relationship, but about 60% of relationship do seems to embed it into the team size itself. And it also, so what this means then, nature was very kind to put us on a cover with the fish plus to think about ecology of research, is what this seems to suggest is this idea of both small and large teams are essential to a flourishing ecology of science and technology. We need large teams to solve increasingly complex problems that require interdisciplinary collaboration, but we should also not overlook the role of small teams in generating new dimensions for us to explore. And this also ties back a recently published Scientific American perspective to think about the social psychology literature in the past century, go all the way back to Ringelmann to think about this speaks to the idea of relational laws, social loafing, common knowledge effect, and to think about maybe one possible remedy is to think about multi-team system recently about, you have a large team, but then embed small teams within large teams, maybe a good strategy. So the idea is when you think about who you collaborate or how do you put together a team, the question is to think about what do you want to do right now? What's the type of ideas? So it's not, it used to have a very simple answer that larger teams is the way to go. This educates me a lot as I work in my own team. It says a lot of times I feel like, yeah, why not? Let's bring in one more person. I mean, it doesn't hurt, right? So at least it doesn't hurt. But what this is showing that it might depends on what you're trying to achieve. As team grows bigger at a phase that wasn't supposed to, that you may be locked into a large team inertia that requires more for you to build consensus. Yeah.
We also passed Dashun on the impact that highly excited particles in some cancer. One of the reasons there are poor human clinical results is because of poor quality of clinical research that we publish in many of these high-profile journals. So just wondering what you.
So different, you mean, can that be sort of the idea of different disciplines?
Do you mean like there's a nice data set which connects patents that cite research papers, and you can put a monetary valuation on the patents. And so I think you're asking what is the real world impact above and beyond the scientific impact?
Yeah, exactly.
So that's a new direction we're now exploring. So we're just finishing a new paper that's try to see what's the overall broader impact of science, especially outside of science. So we're happy to talk more if you're interested. Yeah.
Have you looked at estimating the overall diversity between diversity of constituents? So like looking at individuals that are co-authors that are more like that increase the diversity of the set. Because you say if someone moves from a small to large team, you can look at that relative change and constant kind of fixed effects of that person. And so just wondering is it really about fixed effects or something about the combination?
Yeah, so that there's a wonderful paper last year. I advertised it a lot, not by me, but by Talal Rowan, published in Nature Communications that look at all sorts of the team diversity measures and to show that, given each team size, the diversity seems to increase impact as well. But so there's a wonderful paper about that recently. So they look at ethnic diversity, age diversity, different diversity, and also their collaboration diversity. So definitely.
That page had a lot of work.
Yeah. Collective intelligence. Yes.
So I wonder what sample selection does this, because in analog, we look at companies, we look at what happens to them post IPO. But the thing is that many of these things, they just fail, you never see them. So I could imagine that for the small teams, there are both more of them, you could have lower medium quality. It's hard to imagine you have 100 people working on a project with all crap, right? But one person could do that, it's trivial. And so when you have this large population with low mean quality, a lot of volatility, you can only see that IPO that crosses the bar. Then
Yep.
we can do the statistics and they look very different. But what does that teach me?
Survivorship bias.
You are.
Survivorship sample selection. And it's not literal survivorship, but
Dashun, we've hit 1 o'clock. Why don't you take a minute or two to wrap up?
No, I think he's right. That's the second half of the talk that I have to give by. Next time I'm here, I will tell you a new direction we've been exploring in the past 3 years to think about the idea of failures, because as we understand more about the success of individuals, teams, organizations, and the products and ideas they generate, I realize the big problem is we don't quite have the failure data, and now we do have a bunch of them. So I'll just give you, so survivorship bias, I'll just give you this slides of different things we're exploring. Some of them are published after 3 years, so we're excited to see some of them, including a recent paper in Nature in the 150 years anniversary issue, and also a Nature Communication paper a couple months ago. And these are the broad questions we've been thinking. So if you, and we're actively researching these. So if you have any thoughts and to collaborate, please come to me, including both the causes and consequences of failure that we're trying to understand. Thank you all very much.